This one is, of course, a little different because it's third order instead of just second order. But the main idea here is the same general idea still applies. We're still going to make the same sort of guess. We're still going to guess what sort of guess would probably work here if we have the function and all of its derivatives have to cancel each other out. What sort of function has that property? That when you keep taking derivatives, you get the same type of function and they can be combined.
Oh, just like e to the x? Like, can you just do?
E to the something.
E to something.
Since we don't know what the exponent is going to be, let's leave some flexibility there. Let's say e to the lambda x.
Lambda, yeah, okay.
Where lambda is some unknown coefficient. And then, as before, just like for second order, we would take all the relevant derivatives, in this case, all the way up to third derivative, and plug those in for y and its derivatives. So y prime, we just get an extra lambda. Y double prime, we pull out another lambda and get lambda squared from the chain rule. And then y triple prime, chain rule gives us one more lambda. So lambda cubed is the lambda x. And when we substitute these in for y, y prime, y double prime, y triple prime, every term is going to have what factor in it? What factor will show up in every one of those terms?
The e to the lambda x, or?
Right. And since e to the lambda x shows up in every term, we can preemptively factor that out. If we substitute this into the original equation and also factor out e to the lambda x, we get e to the lambda x times, and then each one of these is just going to have the lambda cubed, lambda squared, lambda, and 1, because we're factoring out the e to the lambda x. So we end up with a lambda cubed plus b lambda squared plus c lambda plus d. In other words, instead of a characteristic quadratic, we get a characteristic cubic. But we still require that that cubic equals 0, because of course e to the lambda x is never going to be 0. So we get this cubic, which must equal 0, and we would call that the characteristic cubic. And the same applies for higher order. If you have a fourth order equation up to a fourth derivative, then you would end up with a characteristic quartic, a fourth order polynomial or fourth degree polynomial. Fourth order differential equation leads to fourth degree polynomial. And generally we call this the characteristic polynomial of that differential equation. Any questions on that so far?
No, I think that's making sense so far.
And then presumably you'd have to solve this cubic. There isn't really a good equivalent of the quadratic formula for cubics. There is a general algorithm for solving cubics, but it's not just one formula. It's a complicated multi-step procedure that nobody bothers teaching anymore because it's way too cumbersome. Yeah. But there are other ways to solve cubics as well. I mean, the most direct brute force method, I think, would just be graph this and see where it crosses the axis. Especially if you have a graphing calculator or computer graphing utility that can find the intercepts to a very high degree of accuracy.
Yeah, I think my professor was saying that it's fine for us to use a calculator or something for that.
As long as you can find some lambda values that make this.
Yeah.
And there's various other methods in algebra as well for doing that, like the rational roots theorem, for instance. But as long as you can find lambda values that work. And for a cubic, how many lambda values would you expect? How many times does a cubic cross the x-axis?
3 times?
Could be up to 3 times. You could have, for instance, a cubic that looks like this. You'd have 3 intersections.
Yeah.
It doesn't have to, though. That's the thing. You might instead have a cubic that is, let's say, higher up and only crosses the axis once. Or you might have a cubic that's somewhat differently shaped. You might have a cubic that, extend this a little bit, if you have a cubic that is shaped like this, where it doesn't really have the up and then curve back down and then go up. If it's just got, like for instance, just the graph of y equals x cubed. It's got this inflection point and that's it. So that's another possibility. You might have only one intersection because that curve around is too high and it's above the axis. Or you might have only one intersection because the inflection point is that intercept and there aren't any other intersections. So we've got several possibilities here. You might have 3 solutions, or you might have only one. I think it's also could be possible to have something like this, where that intersect is somewhere above the axis. Or sorry, the inflection point is somewhere above the axis. So we've got to account for those possibilities. The thing is, though, if in all of these cases, you have at least one intersection. You can't have the case like for the parabola, for instance. It's possible for a parabola to have no x-intercept at all. That doesn't mean the quadratic has no roots. It just means those roots are what kind of number. Like if you had a quadratic whose graph looked like this, no visible x-intercepts at all, and you try using the quadratic formula to solve that quadratic, what sort of numbers would you get?
I want to say imaginary, but I don't think that's right.
The reason every quadratic is going to have at least one root, usually 2, unless it's got a repeated root. The only reason those roots wouldn't show up on the graph is that the graph only displays real numbers. So if the roots are complex numbers, or specifically non-real complex numbers, non-pure real, then that means they're not going to show up on the graph itself because the graph is only showing real numbers. But they still exist, they're just non-real numbers. Likewise over here, this cubic, for instance, it only has one visible x-intercept because the graph only shows real numbers. It's still going to have 3 roots, 3 values that make the whole thing 0. It's just that 2 of those values will be complex numbers. Only one of them is real, and therefore only one of them shows up on the graph. Whereas in other cases, you might have a situation where you only have one root visible because it's a repeated root. Like for example, if you consider the graph y equals x cubed, the only value of x that makes this whole thing 0 is going to be x equals 0. But that's a repeated root. It's x times x times x. So 0 is a root with multiplicity 3. So we've got to deal with these possibilities. We've got to deal with the possibility that maybe the cubic has 3 real roots, or maybe it has 1 real root and 2 imaginary roots, or maybe it has 1 real root that's got multiplicity 2. Any questions on that so far?
Nope. I'm getting it so far.
Oh, also one other possibility we might need to consider. It's also possible to have something like this, where we've got an intercept here and an intercept here. And typically, if it looks like a quadratic at that point, if it looks like a parabola, that suggests that is a root of multiplicity 2. So we'd have a root with multiplicity 1 and a root with multiplicity 2. That is a root that shows up once in factored form and a root that shows up twice in factored form. So we've got to have ways of dealing with all these possibilities. Any questions on that so far?
No, I think I'm following.
So let's take a look at what the results would actually look like in each of those cases. Because we've established that e to the lambda x should work as long as lambda makes this quadratic equal to, or this cubic equal to 0. So looking at some of the possibilities here, maybe we have 3 different roots. Maybe we have 3 distinct real roots. Like for instance, this cubic here. Maybe we have 3 distinct real roots. Let's say lambda 1, lambda 2, and lambda 3. In that case, we would just take the usual approach of e to the power of lambda 1x, e to the power of lambda 2x, e to the power of lambda 3x. And how would you combine those together to get the general solution?
Actually not too sure.
Well, what would you do if it was second order? If you just had two different solutions, how would you combine those together to get the general solution?
Oh, there's a C1, like C1, C2.
Yeah, we would just have.
Okay. I understand. Sorry, I think I was misunderstanding the question.
So some constant times the first solution plus some constant times the second solution. And with the third solution, we just incorporate that into the same idea, plus some constant times the third solution. So our general solution would look like this. Exact same idea as it would be for second order. We just have one extra term because this cubic has 3 roots instead of a quadratic having 2 roots. That also means, though, since we have 3 unknowns, like let's say we know lambda 1, lambda 2, lambda 3. If we want to find a specific solution, we need to find values of C1, C2, and C3. With 3 unknowns, how many equations do you need in order to solve for 3 unknowns?
3, I suppose.
Yeah, we would need 3 pieces of information. So the initial conditions are going to include 3 pieces of information. And if you compare this to first order and second order, for first order, we needed to know y of some value. And that would be enough information to solve for a single unknown constant. For second order, what other information did we need to have included in the initial conditions?
Some value of y prime.
Yeah, we needed to know y prime at some time. Doesn't have to be at the same time, but it usually is. In fact, usually it's just at time 0, but sometimes it could be at a different time instead. Mm-hmm. So for second order, you need to know let's say y represents position. You need to know the position at time 0. You'd also need to know the derivative of position, which would be velocity at time 0. For third order, you're going to need one more piece of information. And what do you think that one more piece of information is going to be?
Y double prime at some time.
Exactly. You would need to know y double prime at time 0, or whatever the time is, which would then presumably be the acceleration at time 0. So these would be the pieces of information you would need. In order to solve a third order initial value problem, you first find the solutions to the characteristic cubic, use those to form the general solution, and then you could use the initial conditions to find the values of C1, C2, and C3. That means you'd have to take the first derivative of your solution and also the second derivative of your general solution, and then plug in all 3 of these values in order to get 3 equations that you can solve for C1, C2, C3. And then, as usual, you would use whatever techniques you want from linear algebra in order to solve for those unknown constants. Plug those constants back in for C1, C2, and C3, and you now have the specific solution that matches those initial conditions. Any questions on that so far?
Nope.
We can also extend the idea of the Wronskian determinant for checking whether the solutions are independent. Because previously, the Wronskian for 2 solutions, if you want to check if those are independent, how would you set up the Wronskian for just 2 functions? Has the Wronskian showed up in your class? Does that look familiar?
Yeah, I just can't quite remember. I'm trying to look over my notes again.
Yeah, because the Wronskian for two functions is a 2x2 determinant, specifically y1 and y2, those two functions as the top row, and then the derivatives of y1 and y2 as the bottom row.
Oh, yeah, okay. So then for this problem, it would be 3x3, right?
Right. We take a 3x3 determinant with the three functions in question. In this case, e to the lambda 1x, e to the lambda 2x, and e to the lambda 3x as the top row, and then their derivatives as the second row. And then what do you think the third row would be?
This is the second derivative.
Yeah, we just continue the same pattern. And this is ultimately because the initial condition equations are going to have an equation for y, an equation for y prime, and an equation for y double prime. And the Wronskian determinant is ultimately just to see if that system of equations is even solvable. If the determinant is 0, then this matrix of coefficients is not invertible, which means we can't guarantee a unique solution for the C values. So the whole point of the Wronskian is to figure out, can you guarantee that C value solutions will exist for any initial conditions? If the Wronskian is 0, then you can't guarantee a unique solution. So that means ultimately that y1, y2, and y3 are not linearly independent. So that's a really good way of thinking of the Wronskian. If the Wronskian is non-zero, then that means you know that the solutions, y1, y2, y3, are linearly independent. On the other hand, if the Wronskian is equal to 0, that means y1, y2, and y3 are linearly dependent, which ultimately just means they're not genuinely different types of solutions. For example, let's say y1 happens to be, just as an example, let's say y1 happens to be cosine squared of 5t, and y2 happens to be sine squared of 5t, and y3 happens to be a constant 1. These would not be linearly independent, even though they look like different types of functions. What would happen if you added y1 plus y2?
I think it's the 1.
Yeah, cosine squared plus sine squared of something is 1. So if these are the solutions you get, then y3 is just y1 and y2 added together. That means that one of the solutions can be written as a linear combination of the others, which means this third solution isn't really new information. You can't have one of the solutions just be a duplicate of the information already provided. You need a third genuinely different solution. So this wouldn't work. These three functions together do not form a fundamental set of solutions. You need a third solution that's genuinely different so that the Wronskian is non-zero. So this is really the main thing the Wronskian is used for checking if you have 2 solutions or 3 solutions or however many solutions, checking if those solutions count as linearly independent. Do you really have enough solutions, or do you have duplicated information and need more information instead? And that extends to any number of solutions you want. If you had a 4th order equation, you'd end up with a characteristic quartic, which has 4 solutions. So you'd have y1, y2, y3, and y4, and the Wronskian would be a 4x4 determinant. And of course, this quickly gets more and more cumbersome to actually evaluate, but the same general principle still applies. Any other questions on that so far?
No, but I think this is making a lot more sense now. Yeah.
All right. So I guess I would say the most straightforward version of this is if you do have 3 distinct roots, because your cubic crosses the x-axis 3 times visibly. Other possibilities would be what happens if you have a repeated root, for instance. Like, let's say you have a repeated root. Like, let's say you have lambda 1, and then lambda 1 again, and then lambda 1 again. Like, let's say your cubic factors to maybe lambda minus 5 cubed. If you factor your cubic and get lambda minus 5 cubed equals 0, then the only solution you get is lambda equals 5. And we would say that's lambda equals 5 with multiplicity 3. Multiplicity 3 means it shows up 3 times in factored form. So in that case, we would have e to the lambda 1x times c1 But we can't just have another copy of e to the lambda 1x, because we need a genuinely different type of solution. So what would we use there as our second solution? Yeah, we can have x e to the lambda 1x. That extra times x counts as a different, makes this whole thing count as a different type of function. And in this case, we need a third one. We can't just have another copy of either one of these. So what would we have instead?
Like x squared.
Yeah, we could have x squared e to the lambda 1x. So this is what your solution would look like if you have a triple root, if you have a root that's repeated and repeated again, or in other words, a root with multiplicity 3. So that would be what you'd get if you have a repeated root, which on the graph would look something like this. Visually, that's going to look like the inflection point is the intersection. Any questions on that so far?
Nope, good.
So if you get 3 genuinely different roots from your characteristic cubic, then it's going to look pretty much like normal. You got e to the something x for those 3 values of something, and then just linear combinations. For the repeated root, if it's repeated 3 times, because you only get one root, which is at the inflection point, then you've got e to the lambda x, x e to the lambda x, just like we saw for the double root in the second order situation, and also x squared e to the lambda x for the third root. For cubics, though, the fact that we've got up to 3 roots introduces another interesting possibility. Maybe instead of getting 3 different roots or one root that's repeated 3 times, we could have a situation that looks like this. So we've got one root that's pretty much normal. And you can kind of see this by zooming in on this region. Near this root, the function looks like a straight line. Straight line is x to the first power. So that suggests it's a first degree, or first multiplicity 1, let's say. But over here, where it dips down, hits the axis, and then bounces back up, near this point, this looks very much like what sort of function?
Just a quadratic. Like...
It looks like the graph of the quadratic if you're very close to this point. And of course, when you zoom out, it stops looking like a quadratic. But zoom in very close to this root, this intersection, it looks almost like a quadratic. So that suggests this root has multiplicity 2. So let's say we have lambda 1 with multiplicity 1, and also lambda 2 with multiplicity 2. As one example of this, you might have something like maybe your cubic factors into lambda minus 3 times lambda minus 7 times lambda minus 7 again. In that case, 3 would be a root with multiplicity 1, and 7, since it shows up twice in factored form, would be a root with multiplicity 2. So this is the sort of thing you see in the factored form, whereas this is what the graph would look like if that shows up. Any questions on that phenomenon so far?
Nope. So I guess for like the actual question, there isn't really a way, because they don't give you like any numbers or anything to determine if the roots are repeated or not. So I guess for that, would you just come up with a general solution for it?
The thing is, there isn't a general solution because there's these different possibilities. So I think what you would need to do there is list out the possible results. You could say,
okay,
set up your characteristic cubic. If the characteristic cubic has 3 distinct roots, it's just c1 e to the lambda 1x plus c2 e to the lambda 2x plus c3 e to the lambda 3x. Versus if you've got a triple repeated root, it's going to look like this. If you've got 1 ordinary root and 1 double repeated root, what would you expect that to look like in the actual solution?
Would it be, so one of them would be just a unique solution. Wait.
Yeah, this one's just ordinary, right?
Yeah, that one's just,
it's going to be c1 e to the lambda 1x. And then we have presumably c2 e to the lambda.
The first one would also just be a regular, no x, and then the last one would have an x on it, right?
We have C3, x e to the lambda 2x.
Yeah.
Since this root has multiplicity 2, it's going to show up in 2 of the solution functions.
Got it.
One of them just e to the lambda 2x, the other one x times e to the lambda 2x. Because we can't just use another copy of e to the lambda 2x.
Okay.
But that's what our general solution would look like. And then for a specific solution, you go through the usual procedure, plug in the initial conditions, and solve. But the important thing is the x e to the lambda 2x genuinely counts as a different independent solution from e to the lambda 2x. And you can prove that using the Wronskian, but you really only need to prove it once using variables. And then no matter what the value of the variable is, it should still work. Any other questions on that so far?
Sorry, excuse me. So I think I got a question about the x. So I understand like why we need x for the third. Actually, it's the third root of like, because we are make sense like that two different answers for the any case. But I mean like why we need specifically x like particularly here to be another.
One way to show that this works is to just plug it back into the original differential equation, and it should end up adding up to 0. But the reason, or the way we got that in the first place was by using the variation of parameters method. The idea is if you know that e to the lambda x is one solution, and you know there's another solution, but you don't know what it is, because presumably, like second order, you have to have 2 solutions. Third order, you have to have 3 solutions. So if you've got another solution and you don't know what it is, one way of finding that extra solution is by assuming that it is equal to the solution you already have times some unknown function. So you would guess, for instance, that y3 equals y2 times some unknown function, let's say v of t. So v of t would be some unknown function. And then to find out what v of t is, you would take all the relevant derivatives of this whole thing using the product rule, because it's a function times a function, and plug that back into the original differential equation. If you do that in a repeated root situation, you find that v of t is just t. Or in this case, v of x would just be x. So you can do this in the reduction of order approach. Assume that the second solution, which you don't know yet, is the solution you already know times some unknown function. And then plug that back in to the original differential equation and find that unknown function. But in general, if the constants are all coefficients, then that extra unknown function is always just going to be times the variable. So times x or times t. Or in the triple repeated root, you get a times x for one of them, and then a times x again for the other one. In fact, as a general rule, both for this situation and also for the undetermined coefficient stuff, trying to decide what to guess, if what you would use for the next solution is already part of the homogeneous solution, if it's already in use as a homogeneous solution, try just multiplying it by x or t, whatever the relevant variable is. That will give you a new type of function to use as a guess. Any other questions on that so far?
Right, thank you, sir.
Then I think we've covered most of these. We've covered what happens if you have 3 roots, what happens if you have inflection point on the axis, what happens if you have one root and then one ordinary root and a repeated root. I think the only one we still need to cover is what happens if you have one ordinary root, but then it never hits the axis again. So let's see what that would look like. So we have something that looks like this. Then we have only one root visible on the graph. There's still 2 other roots. They're just not visible on the graph. So what does that tell you?
That there should be 2 imaginary roots, right?
2 imaginary roots. Or I would at least say 2 non-real roots, because they don't necessarily have to be pure imaginary. They might be a mixture of real and imaginary. So what if there's only one real root? Then presumably the other roots must be imaginary or complex, mixture of real and imaginary. They might be pure imaginary, they might be real plus imaginary, but we'd end up with, let's say, a lambda1 is real. And let's say lambda2 and lambda3 are both complex. But the thing is, as long as the coefficients of the polynomial are all real numbers, complex roots have to show up in conjugate pairs. You can't just have one complex root. You have to have a pair of complex roots that are conjugates of each other. And conjugates just means they have the same real part, let's say alpha, but opposite imaginary parts. Let's say plus beta I and minus beta I. So a complex conjugate pair. In that case, when we set up the general solution, the real root we can just treat completely ordinary. We've got C1 e to the lambda 1x. But for the complex roots, if you raise e to an imaginary power, what sort of function does that turn into? What happens when you raise e to an imaginary power?
Do we have like a real parts and complex parts, like two parts?
Yeah, well, specifically, yes, it will turn into sine and cosine. And that's ultimately due to Euler's formula. Then with Euler's formula, the idea of splitting the, or writing out the imaginary exponent in terms of sine and cosine. If you have e to the power of, let's say, beta x, or beta I x, because we've got the imaginary parts that we care about. E to the power of beta I x, that ends up being cosine of beta x plus I sine beta x. So you get a cosine as a real component and a sine as an imaginary component. If you're talking about a complex root, though, let's say e to the alpha plus or minus beta I x, you can split that up. E to the alpha x times e to the beta I x, because you can split up exponents over multiplication like that. So you get e to the alpha x times e to the beta I x, which we know is cosine and sine. So e to the alpha x times cosine and I sine, with beta as the multiplier on x inside the sine and cosine functions. And so we can do that here. Both of those terms are going to have an e to the alpha x. So the e to the alpha x can actually be factored out. And then on the inside, we're going to have a cosine term and a sine term. Cosine beta x and sine beta x. And then we'll just have linear combinations of those. So let's say C2 times cosine beta x and C3 times sine beta x. Both of those multiplied by e to the alpha x, where alpha is the real part. So this is what your general solution would look like for this situation, where you've got one real root and two complex conjugate roots. Any other questions on that one?
No, I think that's...
All right, then I'm going to get going, but feel free to email me if you have any other questions, and I will see you next time.
Okay, thank you.
You're welcome.